In this previous example 3, this matrix A was diagonalizable. We found 3 different eigenvalues for it, and we only found actually one of the eigenvectors, but you could find eigenvectors that go with lambda 2 and lambda 3 as well if you wanted to. Now, of course, not every matrix is diagonalizable. We saw in 4.2 example 1 that this matrix has no real eigenvalues because multiplying an R2 vector by A rotates vectors by 60 degrees away from their span. So we saw that any non-zero vector x, when you do A times x, you do not get a scalar multiple of x. So no non-zero vector is an eigenvector. And of course, 0 can't be an eigenvector either. But could we find complex numbers? Is there a way we can think of this rotation as multiplying by a complex scalar? Let's see what we mean by that. So if we want to diagonalize A by finding the eigenvalues of A, we want to do the determinant of A minus lambda I and set that equal to 0. And the determinant of this is going to be the quantity 1/2 minus lambda squared, which will end up being lambda squared minus lambda plus 1/4. That minus root 3 over 2 times negative root 3 over 2 gives you plus 3/4. And 1/4 plus 3/4 gives you just 1. So this is the characteristic equation. You could try to factor this by finding 2 numbers that multiply to make +1, but add up to -1, and you will probably fail. But we could use the, what's it called? The quadratic formula to solve this. How does it go? Negative b plus or minus the square root of b squared minus 4 times a times c, right? And divide that by 2a. So this ends up being 1 plus or minus the square root of -3 divided by 2. Now, the square root of -3 is I times the square root of +3. Because remember, I here is the square root of -1, and all divided by 2. So these complex numbers are eigenvalues. Let's find eigenvectors. So let's say we're talking about lambda 1 is 1 plus I root 3 all over 2. Maybe it would help to write that as 1 over 2 plus I root 3 over 2. If we want to find an x vector that is a eigenvector that goes with this, we want to do 1/2 minus this, which will be negative I root 3 over 2, root 3 over 2, negative root 3 over 2, and same thing down here in the bottom right. We want to do that times x and get 0. That x will be an eigenvector. Okay, so what I notice here is that column 1 and column 2 are almost the same. It's just that there's like a factor of I missing. So if you think about how to make this work, you can just sort of try stuff. So we want to do this number times the first column and this number times the second column and make them add up to 0. So maybe we could make them become opposites. Let's see. I noticed that this is root 3 over 2 and this is negative I root 3 over 2. So what if I made x1 equal to just I and x2 equal to 1, that will make root 3 over 2I minus 1 I root 3 over 2 equal to 0. So that part works. And also, if you do I times negative I, that multiplies to make positive 1. That makes the first component come out to be 0 as well. Okay, so that is an eigenvector that corresponds with lambda 1. Let's do the same thing with lambda 2, which is 1/2 minus I times root 3 over 2. And in this case, we want to make our eigenvector y1, y2, when multiplied by a minus lambda 2I, will be like so. And again, thinking about what you can multiply these columns by to make them add up to 0, it looks like I negative 1 would work. Now, this doesn't make sense if you just try to think of it as 60-degree rotation in R2, because these vectors are not in R2. They are in C2, where C is the set of complex numbers. And just looking at C1 is in a sense like a two-dimensional thing. You have the real number part and the imaginary part of your complex number. So any individual complex number already has like 2 dimensions. So if you're going to try to graph these vectors in C2, you kind of need 4-dimensional paper for that, because you have 2 real dimensions and 2 complex dimensions. And it does turn out that multiplying by this complex number does do a 60-degree rotation. It can be shown that this lovely fact here is true. Euler's identity, that e to the power a plus bi, the quantity, times t, is the same thing as e to the at, just a regular old real number exponential part, times the quantity cosine of bt, plus I, the imaginary unit, times sine of bt. Which leads to cool facts like e to the power pi I is equal to -1, for example. There's a really good 3 blue, 1 brown video that demonstrates why this is true. I'll try to remember to put a link in the description for that. So, yeah, complex numbers can represent rotation, and multiplying C2 vectors by these complex numbers is rotation, and it's also matrix multiplication, but it doesn't have any real eigenvectors or eigenvalues like we saw here. It doesn't work in R2. But if we allow for complex numbers, we can find a lot more solutions of these difference equations. By the way, solutions of this we showed were of the form yn is a to the power n times your starting point. Now it turns out differential equations, linear differential equations, can be written in this form. This is a thing you'll study in a standard ordinary differential equations class. It turns out they have solutions that can be written in the form y of t equals e to the power a t times some initial conditions vector. But you might be thinking, what the heck is e to the power at? What does that mean? Well, it turns out if you take the standard Taylor series for e to the power x and you just replace that with at, what you get is 1 plus at plus a squared t squared over 2 factorial plus a cubed t cubed over 3 factorial, and so on. it turns out this gives you a nice way to describe solutions of any linear differential equation that can be written like this. So anyways, that is as far as we're going to go in complex numbers in this class. You don't really need to know any of this for a test, in my class anyways. I just thought it would be cool to kind of get a preview of slightly more advanced math than what we're doing here. In the next video, we'll look at theorem 4.5. I'll see you then.